Introduce Nicola Yawaniki. He's going to be with us today, tomorrow, and Friday
Yeah.
with some lectures related with PCB design and taking into account machine learning applications. Nicola is currently working for Teledyne in Netherlands. So, Nicola, the floor is yours.
Okay. Thank you very much for the introduction. Yeah. Good evening or good afternoon, everyone. Here from Eindhoven, from Netherlands. Let me firstly introduce myself. As Romina said, my name is Nikola Jovalekic, and I work as a senior system development engineer for Teledyne Technologies in the division which deals with the X-ray imaging. I have a background in electrical engineering, and I also have a PhD in electronics. On top of that, I have more than 17 years of experience in different industries. So when I started to work, I was initially working in optical transmission systems in R&D as a hardware designer. After that, I moved to another field, which was dealing with marine electronics. I also worked in R&D department, and we were developing the devices which are used for tracking fishermen vessels. I was mainly dealing with the hardware design, with the design for EMC, and with the wireless communication part of the device. Then I switched to another field. I moved to International Atomic Energy Agency, where I worked mainly on developing gamma detectors. So I was dealing on a hardware level and on a system level as well. And after that, I moved to automotive industry, where I was working on level 3 autonomous driving systems. And finally, after that, I came to Teledyne. Yeah, so as you can see, there is some experience on my side in industry. And why I'm saying this, when I was talking to Romina how we are going to tackle this workshop, we were thinking in two directions. The first direction was that we also cover some hardware design aspects in edge machine learning devices. That was the first thing. And the second thing was that we also would like to provide and give you some of the experience from the industry and how that actually fits into this whole story. So from my side, you will hear some mixed story. There will be like theoretical stuff, but that theoretical stuff will be also mixed with real experience from different industries. So you will not get bored when the theoretical part will be presented. That's one thing. The second thing is I will explain you a bit how we imagine that this part of the workshop will function, so that you can focus on some parts. First of all, we understand that this group is mixed group, so there are people with different backgrounds, and of course we cannot fulfill the desires of everyone. So we tried our best to make this interesting for most of the people. On some places you will get bored maybe, but on some places you will be very interested to hear what we have to say. So the workshop, this part of the workshop is organized as follows. Firstly, I will give you just an overview of the embedded platform architectures used in edge machine learning devices. And I will also cover some key components. This is just a general story, just to give you, let's say, some hardware-based introduction in this topic. Then we will move slightly towards the design. Why towards the design? Because I would like you to understand some processes in terms of the design, and you will see why. I will firstly introduce some methods which you are using when you design hardware, and you will actually see the methodological approach to designing. It will not be boring because I will give you some extensive examples from industry, how it works in industry. So you will see that there is a big discrepancy or a big gap between what we theoretically actually know and what we actually do in industry. I'm going to be critical. I will tell you the bad sides, so not the good examples. And this is most probably something that you will face when you become a full professional working in industry. So this will also be helpful, not only in a technical sense, but also in a sense to use it in your career advance as well. Then when we finish with let's say methodological part of the hardware designing, we will then switch to something more practical, and we will consider practical parts of the hardware design. I will do that on some example which is real, which I worked on, which was developed and produced and also tested. I designed hardware for that part of the firmware as well. Romina for that wrote some algorithms, but you will see later on what I'm talking about. And when we finish that part, so when we consider these practical aspects, I will do simple demonstrations. First of all, I will show you something in a CAD tool which is used for such a design, and I will go through some examples and some parts of the design. You don't need to memorize that. You don't need to try to fully understand everything if you don't have a background there, but it is good to see that. And why it is good? Because it will just give you an impression, actually, what's going on behind the scene, what's going on in hardware. And that will help you tomorrow when you start as a industry professional to better understand the problems and to collaborate with different teams more efficiently. And then when we finish sorry, that part, then I'm going to tackle some more advanced problems, which are actually problems of the whole industry in that sense. Of course, I'm not going to go into very detailed presentation and analysis and solutions for these problems, but again, my goal is to give you a rough impression so that you know what the hardware designers are dealing with if you are, for example, ML engineer. So as you know, these guys, they are basically always involved just like in their part. Okay, we are going to deal with algorithms, we are going to deal with this, that, but we are not going to deal with the hardware and the platform because, yeah, this is something we, take it as granted. We will just execute our algorithms and that's all. And after that, I will give you some live demonstrations. So I will show you how you can efficiently debug some of the problems, and I will do that on a live hardware. I will be streaming that from here. So in that sense, I will try to, let's say, fully round something from like just an overview to through the methodology, through the real practical example, concluding that with some live measurements and demonstrations. I don't expect you to go out of that room and to remember everything. It's not the goal, and it's not possible, of course. And on my side, it's not possible to present you everything. I try to select some important things which I find important based on my experience. But the main goal at the end will be that you have a rough impression and that you understand some other, let's say, problems which are not related only to ML engineering, for example. I advise you to be more or less careful. If you do not understand something, feel free to stop me anytime and ask whatever you want. If you have maybe troubles with English, Romina is there, she can translate, so we can also bridge that kind of gap. And after we finish all this, we will have one exercise. And that exercise will be the following. So you will have 1 hour for the task. You will be required to draw an architecture based on some requirement specifications I will provide to you. And after that, you can do that on a piece of paper, for example, and then you will just submit that. And after that, we will analyze all these solutions. And I think for the best solution, Romina has some kind of prize, I would say. So be focused, be focused. And if you have questions, just stop me. During the presentation, I will have some questions for you. And also on my side, I will have a, let's say, whiteboard, which you will be able to see on share screen. So this is more or less what I would like to say before we start. And just the last question, in order to tailor this presentation for the group, I would ask how many people in this room have background in electronics? Okay, most of them. Good. So we are then on the right place. Okay, people in algorithms in ML, so not related to hardware, to electronics. No such people. Okay, so Romina's part of the workshop was actually very useful for you, but this one will be also, I hope. Okay, so you are all students, or almost all students. Yeah. Okay.
Not all of them. Yeah. So it makes
Okay, no problem. So yeah, I will now share my screen and we will start this. Okay. I will just need more thing. Okay. 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 So first of all, just to see if this works. Yeah. Particularly the objective of the whole presentation series, I already give you that. Then we are going to tackle a bit significance of understanding the underlying hardware in ML. After that, we are going to talk about the architecture of generic embedded systems. At that point, I will need a bit your help. After that, I will talk about limitations of these traditional embedded system architectures they have in ML application, in edge ML application. Keep in mind that we are talking all the time about that, not about clouds and I don't know, server centers or whatever. After we address the limitations of traditional embedded system architectures, then I'm going to tackle a bit key hardware components and some of the common architectures that are used in ML, and we will cover their advantages and disadvantages. And then we will just conclude with some major conclusions. And that will be all. So this should be like a very easy and simple part to cover. So to develop and deploy algorithms effectively, it's beneficial to understand the hardware where the code runs. A good grasp, of course, of the hardware platform offers several advantages. First of them is, of course, performance optimization. So if you really understand the underlying hardware, you can tailor your code. You can tailor your algorithms to the certain platform. And if you do so, then you can expect that you have an optimized solution or better solution than, for example, the competitors in the industry. This is very important, and this is something which is sometimes neglected by the people who write code. So they don't take this into account, and they just encapsulate themselves in what they do, and that's all. If you really understand the underlying hardware, your code will be compatible with the platform, and you will be able to properly control the platform. You can imagine that this is very important. This is something which is in industry solved in this problem. Usually, hardware designers will provide for you so-called hardware-software interface specification. So you will get some specification from hardware people, and you will just rely on that. But in practice, if you really want something optimized and compatible with the hardware platform you're working on, you really need to understand more than that. And usually, that's not the case, as far as according to my experience in industry. Of course, if you understand that, you can make it efficient. You can really make it efficient, and you can really exploit the maximum of the platform. Very important thing is troubleshooting. So you can imagine the situations that your device is already deployed in the field, which of course happens in industry all the time. But what happens also all the time is that these devices, they come back due to some failures, due to some problems. And what usually customers wants the designers team, first of all, the support teams, is to see where is the problem. Sometimes support team cannot see where is the problem. And then that will be escalated toward the design team. And then the designers come into the game of the troubleshooting. If you don't understand the platform, if you don't understand the underlying hardware, your troubleshooting will not be efficient, if possible at all. And that's, let's say, joint effort of hardware team and the firmware team. From my experience, not always firmware team was able to give efficient inputs. When I say efficient inputs, it means that they needed time to get acquainted with the platform. But they acquainted with the platform at the point where the device is already deployed and comes back due to some problems. So keep in mind this is a very common problem. And of course, scalability. If you understand the modules, if you understand the particular subsystems of the hardware, then you can, let's say, not in a difficult way, make a scale up of the platform if there is need for that. Okay, so now I will go further. Understanding hardware design problems can significantly enhance cross-functional team collaboration for ML algorithm and code developers. This is a very, very common problem in industry. So what you will see as a professional when you start working is that the different teams, especially hardware and firmware teams, they have problems with each other. Why? Because when there is some problem, based on my experience, firmware designers, if they cannot see the problem, they will try to put the problem on the hardware side. Hardware designers do the same, and then the collision actually happens, and the efficiency of the solving the problem really decreases. So the time needed for resolving the problem is extremely increased. But if you really understand what's going on there, then we come to this point. Teams, first of all, can communicate more effectively since they use shared language. They understand each other's language. That's very important. In order to understand each other's language, you really need to know at least something. And this is the purpose of this workshop. After this workshop, you will understand at least what's going on in the hardware team. Okay, you have a background in electronics, but yeah, you will now hear the stories and examples which are from the industry, and you will understand the real problems, and you will be able to face them properly when you encounter them when you start your professional career. So knowing hardware constraints and challenges allows ML developers to propose solutions that are feasible and optimized for the hardware. This is clear. And there is one very important aspect. If there is a common language between these two groups, between these teams, then there is something which is called synergy between these teams. It's a rare, but it happens. And that happens when these teams understand each other problems. And these teams really perform the best in industry. So keep in mind this when you start your professional career. Okay, now we are switching to something more technical. And we are going to define the architecture of a generic embedded system. Since you have a background in electronics, I expect now you to tell me how to sketch the architecture of a generic embedded system. Whatever or however you see it, just say, and I'm now going to share my whiteboard so that I can draw what you actually say. Just a second. Okay, we are there. Let's do like this. Okay. You saw the beginning, but okay. So as you saw, what would be the main component here? Processor, yeah, that's of course something we need. I will just put it like this, as you saw on the slide.
Sorry, just a thing. We are not seeing the screen.
We don't see the whiteboard.
Okay. Don't see the whiteboard. Okay, just a moment. Okay. Okay, it works better if I share. Okay, a second. Now it's okay. Here we are starting in a second. Okay, 5. Okay. So now you should see the last slide. Yeah, okay. That's good. And I'm going to do the following. I will just finish this. Yes. Okay, and then we switch to whiteboard. And I wrote, yeah, okay, we are there. I will just remove it. So someone says processor, I will just mark it as a CPU. Okay, we have a main component. What else do we have in that, let's say, classic common architecture?
FPGA.
FPGA. Okay, I will draw it somewhere here, let's say, not to collide with the CPU. So we say FPGA. Okay, what else? Memories. Yeah, it's obviously needed in most cases. I mean, of course, it's always needed. Let's put it here. Then
Access or I/O.
I/O. Okay, okay. We can say I/O. We can say yes, I/O. Yeah. We can say that maybe we can call it like peripherals, some peripherals, which are connected through these I/Os, for example. Okay, then power supply, of course, that's something we cannot work without. We'll put that here. By the way, I like power supplies. That's a very nice topic. Sorry about my handwriting. It's not easy. Okay, let's go further. We need more things in order to have our common traditional embedded system working.
Clock.
Sorry?
Clock.
Exactly, clock. Good.
What else? To connections, buses, and those things, or are we leaving those out?
Yeah, we can say some buses. What buses would you mention?
I don't know, CPU memory. I mean, there will be buses everywhere. That's why I asked if we need to take those into account for this exercise.
So just to repeat if I understood properly. So you are mentioning buses between processor and memory.
For example,
Okay, yeah, that's something we of course need. And we can just put like something like this.
should we pay attention to those stuff, or only the blocks needed for maybe?
Yeah, let's just do the top approach. So we don't need to tackle these, let's say, details at this point. So do you have something else, something more here you would like to add?
Wireless communication.
Wireless communication. Okay, let's put wireless communication. What kind of wireless communication would you put?
Bluetooth or maybe Wi-Fi.
Wi-Fi. Okay. So let's say like this. RF module. Wi-Fi, for example. Okay, Wi-Fi. Do we need something else in order that this system work?
Is storage included in memory?
Storage. Yes. You mean storage for FPGA configuration?
Yes, I think, or yes.
Yeah, we can put like some not flash for that. Okay, how would you debug this application? Yeah. So you need something to download the code, and you need something to debug. So we need something to fetch from that. Let's say something like this, maybe. Okay, so we have power supplies. That's something we need. Of course, we need clock. Without that, nothing will work. That's also. So we need memory. We need memory to store code. We need memory to store data. That's okay. We also need some peripherals there. So we need some IOs, which will be used to connect to our peripherals. Then we need something to debug. Yeah, we need something like serial wire debug or JTAG, whatever. Do we really need FPGA? Maybe yes, maybe not. Do we need Wi-Fi or any kind of wireless communication? Maybe yes, maybe not. But the core is always the same. The core is always the same. So I will just back to my slides. Here. Okay. This already mentioned. Some peripherals, sensor and data. This is basically generic architecture. This is generic architecture. Just a moment. Okay, so this is something we will always have in any kind of system. Basically, more or less, this is it. But let's now address this. We want to use this in ML applications. Let's address it. Let's see what's going on there. So if we want to use this kind of applications, we will have a bottleneck. And that bottleneck is actually memory bandwidth, also interconnect bandwidth. Do you know why? Yes?
Yes, no.
They're very slow.
Because of the speed, there is a constant increase in speed of processors and the amount of data we use to process and to do stuff.
You are on a very right track. So I will share with you one diagram. This is very important to understand, and this is why we have shift towards some other architectures. So in this diagram, I will just turn on the laser pointer to be. Do you see the laser pointer? Okay. So what we have in this diagram, we have the following. We have here processing power in black. We have a floating operations per second normalized. So these numbers are normalized. And you see the trend. You see the trend from 1996 towards 2024. This is the trend. Then in green, this is the trend of memory bandwidth. So green. And in blue, we have a trend of bandwidth of interconnects. So what we are talking about here is that we are able to increase number of floating operations per second, as you can see here, 3 times in 2 years. But bottleneck actually is created here because we cannot increase this bandwidth towards the memory. It's only 1.6 times per 2 years, and interconnect bandwidth is 1.4. When we talk about interconnect bandwidth, we refer to different physical layers and protocols on top of that, such as PCI Express, which is extensively used, and NVIDIA Link as well. So these interconnects are actually made on a hardware, on a printed circuit board, and they have their own limitations there. And what happens in industry is that engineers cannot even achieve these speeds which are specified by the standard due to poor design. But we will tackle that later on. So we identified the problem in the main traditional architectures. We identified the bottleneck. More precisely, what's going on there is the following. As you can see here, this is a processing unit. Okay, you have cache memory here, you have ALU here, and you have external memory. Bottleneck is here. Even if you have cache, you need to fetch data, you need to fetch instructions, and you need to store them in cache. You will also have a bottleneck here. So as you can see, the transfer of weights and intermediate data between on-chip and off-chip memory and processing elements increases latency and power consumption. Power consumption for edge devices can be critical, And then we have a problem. Optimizing energy efficiency is a paramount in advancing the development of intelligent edge devices. And this is the problem. It can be resolved in different ways. So I will just briefly go through the some architectures and some specialized components which we can use to address this. We can categorize the architectures based on a primary processing component criteria. This is one of the criteria we can use. But before I just divide this into the groups, I want to tell you something, how you can actually generalize this and abstract this. Basically, today, everything is system on chip. We can call everything system on chip. Even microcontrollers, for example, from STM, they have a family which has some hardware accelerator on it. It is small. It is not as powerful as, I don't know, GPUs or some NPUs or whatever, but it has it. So it's a very tiny, but it is system on chip. However, I made some classification here. So we have a microcontroller-based architectures, system on chip architectures. This is generalized. Actually, everything is system on chip nowadays. Field programmable gate arrays architectures, neural processing unit architectures. Now I will just run through these architectures and I will just show you the minimum requirements on the hardware and the common, let's say, set of components which each of these architecture require, as we did for this traditional architecture. So first of all, there are several reasons why microcontrollers can be advantageous for specific applications. Real-time processing, we can do that. Specialized processing capabilities. You can have some small hardware accelerators and DSPs on microcontrollers. We have a compact size, of course, and it can be also integrated. There are so small microcontrollers that they can be like integrated on wearables easily. They have inbuilt security features, encryption, secure boot, and so on. And they have strong community and ecosystem support. These are the main advantages, but we cannot use them if we cannot deploy our algorithm there, of course. I will not repeat this. I will not mention this because this applies to every single architecture, and this is the first condition we need to consider. Okay, so this is just a typical architecture where the microcontroller is very easy, actually. These series are from STM. They have some hardware accelerator inside. Of course, you need something to debug and to download your code. You need a clock. That's a must for everything. You have some peripherals which are utilizing these slow speed or low speed buses like I2C, SPI, UART. And you will have some sensors or actuators, some very small. Power supply. Why I put this like these power rails here? You see that even for microcontrollers, which are considered to be the simplest one for these applications, nowadays have a, let's say, not straightforward power supply scheme. You have different rails, and not only different rails, you need to control the sequence of turning on and turning off these rails. So you need to sequence. You usually will use some specialized so-called power management integrated circuit or PMICs to do this job for you. And they are usually programmable. So you can set the delays, you can set the ramp up, ramp down, and so on. Depends on the complexity of the PMIC. You can do that. Let's just quickly go through the others. System on chip integrate multiple components into a single chip, providing a compact and efficient solution for edge ML devices. Yes, as we already said, we can actually everything considered today as a system on chip, basically, if you ask me. So there are several reasons, like for the microcontroller based. So integration of components, we have on the same silicon, we'll have CPU, GPUs, memories, various peripherals. You will see later on, I will present you a very complex thing in this sense. Performance optimization, of course, we have everything on the same silicon. Space efficiency, we don't need to design these buses and these interconnects between these components, CPUs, GPUs on the PCB. Rather, it is already in the chip. And that makes the design and more easy. And of course, we have space efficiency. Reduced latency, of course, due to obvious reasons. And as I said, easier integration in the system, because it can become a nightmare to connect these components on the PCB, because you are in the domain of very high speed digital designs. They have their own design principles, which really differs from traditional, let's say, hardware design for lower or low speed. Okay, so let's see some typical architecture of edge device utilizing a specialized SoC. This is Jetson Orin from NVIDIA. This is a module. I worked actually with this module when we were developing level 3 platform. It was the development platform from BMW, and there were 2 of these in the system. This is a big module. It requires its own cooling system. It has very high power consumption, basically. You need to provide all these peripherals to this. And this was a part of the system where there was also a very powerful, actually 2 very powerful CPUs in the systems. So as you can see, this is not only meant for, I don't know, some clouds or some server centers. You can make edge device also with this kind of components. But this component was very big, physically big. It was in the trunk of the test vehicle. It had a liquid cooling, but yeah, we can consider this in the light of edge device. It's also possible. Then you talked, I know that Romina was mentioning different SoCs, but she was mainly in FPGAs, which has also some cores next to FPGA in the same silicon, CPU cores. Here, this is just FPGA without anything, like, for example, RTX series. So FPGAs, they offer reconfigurable hardware, allowing for custom implementation of ML algorithms. You already discussed this thoroughly with Romina, I believe. There are several reasons, as with the previous architectures. So customizability and flexibility, of course. Parallel processing capabilities, low latency, not as in ASICs, but still low latency. Reconfigurability, very important. And relatively straightforward integration with other components. Okay, to understand the power tree, how it looks like for this is like for ARTIX. You see there are different power rails here. Different power rails, and it's very important that you have a proper sequence to turn on and turn off the system. You see, this is the same as what we have in microcontrollers, which have, for example, small hardware accelerators. Basically, it is the same. The paradigm is the same. If you understand microcontrollers, you will also understand this in this sense. Yeah, this is just a typical architecture, nothing special. All the systems based on FPGA needs to have this. The only difference with the, let's say, the peripherals, if you compare it to microcontrollers, you now see something else. You see these high-speed links here: PCI Express, USB 3.0, and Ethernet. That's because, of course, FPGA can support processing of this. Of course, in contrast, you need some NOR flash external DDR. Clock generator must be faster, and so on. And sometimes, of course, you need also a cooling system there. Okay, MPUs. Again, we can talk about system on chip. They have this is a different hardware accelerator. They are used in specific ML algorithms. As it is here written, in addition to specialized subsystem for mathematical operations, these components also include additional modules on the same silicon as SoCs. Basically, we can also treat it as SoC. And the same things for power supply and peripherals needed to operate applies. As I said, the integration of these components is as complex as that of SoC. This is something from Halo. I didn't write that here because I can't, but you can. I just wrote MPU, and this is power supply tree for that. As you can see, you have here different subsystems. Of course, it's much more complex than a microcontroller, but the paradigm we use is basically the same. You have some sensor interfaces. This is for video. You have some small peripherals here, UARTs, GPIOs, JTAG, timers, memory interfaces, QSPI, serial data I/O, data interfaces, USB 3.0, PCI Express. You will always see this when you have high performance SoCs. And then you have vision subsystem, of course, neural network core subsystems, and these are some cores, some ARM cores there. You have them also, I would say, as a housekeeping for this piece of silicon. Okay, this is just concise comparison of various architectures based on their computing components. So I categorize them like this. Yeah, so CPU only, CPU plus GPU, CPU plus NPU, FPGA based. We already mentioned them. This is just summary of that. We are not going to tackle this because we already mentioned that. And I will just give you major conclusions. Just some takeouts you should take from here. So first of all, we were talking about something which you will use as a professional industry. So efficient cross-functional team collaboration requires that team speaks each other languages and understand basic principles and constraints. That's very important. So you will make your life easier, and most probably you will make your advancement in career bigger. All common edge ML architectures actually have in common that they suffer from memory and interconnect bottlenecks. They simply suffer. But there is Sorry? Okay, never mind. There's a major shift in processing architectures, such as in-memory computing. I was just mentioning. So what is going to happen in a near future, and the company like 3 floors below me, Accelera, is working on these kind of things. They are shifting these let's say processing units in the memory, so that will be in place together, and then using some special techniques like through silicon vias and special interconnects, you will be able to do everything in the same place, so store and compute. That's where this most probably will shift towards. Okay, so I think we are a bit over time, yeah. But do you have any questions before we go to short break? Okay, I think that's no. Okay, so see you in 10 minutes, let's say.
Okay.
Okay. So now I will just start with another topic. Yes, we are almost there. I hope that you didn't get bored on the previous one. Now we are going to delve a bit deeper. Yes, this one. Okay, here I am. Then, okay. Yes. Okay. Do you see a screen? Okay. So this can be a very boring topic. If we cover methodological approach to design embedded platforms for machine learning from perspective of, let's say, from the theoretical perspective, this can really be boring and useless for most of the people because they cannot focus on this. And what also happens in practice is that this methodological approach is not applied almost at all. The reasons for this are multitude. You will always hear, yes, we didn't have time. We were under very stringent time constraints, so we could not apply each step and this. But that always leads to catastrophe on the project. And yeah, I was part of such projects in the past, and the most probably I will be in the future. But okay, let's see. Just to see if this. Okay, we are there. So to systematically address the challenge of designing an edge machine learning platform, we should break down the problem into smaller manageable parts by abstracting its complexities. That's you can remember this can be applied everywhere, not only in this hardware design, but everywhere. So if I would ask you to tell me how would you tackle like methodologically the hardware design for ML application, what would be your answer? How would you formulate that? How do you see that? Let's say from the perspective of the student, let's say like that. What would be the very first thing you would do when you get the task to design certain platform?
Maybe analyze the data.
Analyze the data. Is that the answer?
Well, you have to, I think, see the specifications and see what parts or blocks you're going to be working with.
Mm-hmm. But let me rephrase my question. So you are the part of the team which needs to develop a certain platform, and you have a customer request. So you are not like sitting at your desk and thinking about what to develop, but you have some constraints, and the major constraints comes from the customer. So customer wants a specific system. Usually customers are not the people who are technically in the field, but they more or less know what they want, but they don't know it precisely in technical sense. And now you are part of the team which needs to develop such application. That would be my question. Let's put it like that. So you are part of that team. You are now talking to the customer, and you need to develop a platform which is requested by the customer. The customer knows more or less in general what he wants, but he doesn't know the details. And now you need somehow to come to these details. And of course, not to come to the details, but you need to design a whole platform. So how would you tackle that? How would you approach that?
My first step would be to see if there's something similar to what I have to design already in the market or some similar product. See if I can find more information.
Oh, I'm afraid I didn't hear well.
So basically, like find more information if there's a similar product on the market already, and try to research beforehand.
Okay, that can be approach. That can be approach. I mean, the beginning, the very beginning. That can be, but you know, you work in innovations. You really work innovations, and there is no similar. There is no similar product. Because
translate the thing that the client wants to a problem, I guess, to a specific problem that you know. I think that's the difficult part because you need to translate what someone is saying in a common language and you need to translate it to a technical and electronic language and say, I need this system, I need these things, or to make these steps to get that system.
exactly. That's the exact answer. Exactly. And that's the main problem, basically. That's the main problem. So I will tell you, I was working on a project now. It's almost done. Translating this from the customer to the real requirements took us more than half a year. Yeah, it's really like that. And it's very tough. It's very tough to do that. So I would say that you firstly need to analyze the requirement put by the customer, and that's exactly what you said. So we will put that as a first thing here: requirement analysis. So once we get there, when we analyze, then we need to do something which is called system architecture design. System architecture design. This is also a very, very complex task. And usually you will have a single person in the team or two persons which can tackle this. Then when we finish with the system architecture design, then we go to the detailed design. So to the detailed design. Detailed design, when we finish that, we will tackle later on what's that. We go to the prototyping. So then we build the prototype. After we do that, then we are going to firmware development. When we finish firmware development, then we go, of course, to the optimization. When we finish that, we go to testing and validation. And then we go to design preparation for volume production. And of course, after that, we have production and deployment. These are the steps. These are the steps, and this should be applied whenever you can. Otherwise, you will delve into unstructured design and you will make mistakes. We'll make these mistakes because complex projects cannot be handled without structure. It is not a project where you have like one simple board or whatever, and then you develop something, you put on a table, you test, you show, and say, this is it. No, that's in industry, that's not even called a prototyping. It's called like maybe a pilot if something is doable. But these are all the steps you need to apply. And you will face that when you start professionally working. You will face these things, especially in a big company. Okay, so let's delve into requirement analysis. What we do there, actually, what we do. So when we talk to the customer, we need firstly to understand what he wants. There is a gap in communication there because they cannot translate their requests and requirements into technical language. So very skilled, very experienced engineers, developers need to go there to talk to them and to try to understand what they want. So then, based on that, we will have functional requirements. So we define the specific task the embedded system needs to perform. And we need to agree on that. What happens in practice is that customer changes these functional requirements. They start with something, they succeed to formulate that together with the technical team. And during the time, like after some time, they simply change something because they heard something, they saw something new, they change it, they simply change it. And that can really influence the workflow on the design. There are also non-functional requirements. So these are non-functional requirements. What does it mean? We need to consider performance, power consumption, size, cost, and reliability. This is what customer will want to hear. So how you are going to tackle this. And they will not think in a technical sense, they will think in some other senses, usually. And there will be a lot of discussions, not to say collisions. But okay, once you confirm this somehow, now you maybe partially understand why, for example, for us took in the last project so long to define these things. Then you come to the constraints. So here I wrote like identify any constraints such as environmental conditions, regulatory requirements, and compatibility with other systems. Okay, you understand environmental conditions. So you need to understand where you are going to deploy your device. Is it like somewhere outdoor with a high humidity, with a lot of rain, or it will be some indoor, or it will be like in some laboratory or some building or some other environment, whatever. That's easy to understand, and this part goes more or less easy. But regulatory requirements, this is actually very tricky because you need to understand which regulatory requirements are to be applied to your device. You need to categorize your device into something which is actually to be applied certain regulatory requirements. This sounds easy, but actually it's not easy. There are special teams in bigger companies which deals with that, or smaller companies, they simply take external companies to identify regulatory requirements for that. So believe it or not, this is a problem. And also when we talk about compatibility with other systems, this is mainly about electromagnetic compatibility. There are a lot of standards and categories of the devices, and you really need to understand based on your based on functions the device performs, in which category that device can be put. This is also a problem, and there are external companies in smaller companies which deals with this topic. For example, here at Teledyne we have a dedicated team for this. Okay, so once we finish this requirement analysis, we succeeded to translate customer requirements to requirement specification and so on. We then proceed to so-called system architecture design, as we mentioned. So what we need to do in this part is to create a high-level block diagram of the system showing major components and their interactions. how they interact with each other. Remember this, because this will be one of the major tasks for you in a lab exercise on Friday. And the winner will get the prize. So it's worth to understand this and to remember. Okay, so, but this is very important, because if you do not understand how these components interact and how they should interact with each other, your system is not going to function according to the requirements. That's a problem, of course. After we finish this high-level design, and that is, as I said, usually done by a dedicated person, which is called system architect. At Teledyne, it's not called system architect, it's called the senior system development engineer. That's me in this case. Then you go to the point where you need to select the key components. So you need to choose appropriate processing components, memory, peripherals based on the requirement. What does it mean, key component selection? You need to come up with a certain part numbers. So you have a component, you cannot say FPGA, you need to specify which FPGA, exact part number, and so on. Everything needs to be specified. Okay, so then we go to something which is called interface design. So we need to define interface between different components and subsystems, define the communication protocols. What do you think? What do we define here? Can you give me some example, for example, from some embedded system when we need to define interface design? Can you tell me some interfaces? How can we deploy them? In which, for example, situations?
Well, for example, if you have a sensor that has like a SPI or a memory with SPI bus, and then you have to connect that with the CPU.
Yeah, that's for example one application. How would you classify SPI, as a high-speed interconnect or a low-speed interconnect?
Well, with the bandwidth of today, I'd say low speed.
Low speed. Yeah, that's correct. When do we use other interfaces? Actually, other low-speed interfaces. Can you also give us some examples of that as well?
Well, you have I2C, you have CAN, Modbus. It depends on the component or the protocol that you want to use. Maybe if you want to connect with another system, you use Modbus, for example.
Okay, yeah. That's yeah, that's on the lower side, of the speed. If we talk about ML applications, we will also need the high speed interfaces as well. We mentioned some of the high speed interfaces. We mentioned them. But do you know what is the major problem of high speed interfaces in terms of interference in the system?
I think the first thing that comes to my mind is distance. It's like, it depends on the application. If you want to connect like a ton of sensors and they are spread out in like some distance, you automatically need to rule out the fastest IOs. I mean, that's the first thing that comes to mind.
Okay. I will tell you. So interface design is extremely important. And when you do the design, you really need to plan these interfaces very, very carefully. especially interfaces toward outside of the system, especially. That's extremely important and very, very, very critical. You will find out later on when we delve into the things even deeper. At this point, we will just say like this: system architecture design, milestone, very important thing. So you have high level design where you create just a block diagram. You know that you will use, I don't know, like a CPU, you will use microcontroller, you will use FPGA, whatever. You know that you need to use, as we saw in these generic architectures, all these components which needs to provide the operation of these of the major components, key components. Then you will have some peripherals, you will have some connectivity, you will have some interfacing, and so on. When you finish that part, you go to key component selection. Also, you will face there different constraints when you find the key components. Then maybe you will face the constraint from some other department, which will say like, okay, your bill of material, that's how it is called, is very expensive. We cannot sell these kind of devices. You need to change this. Even sales team of the company can influence your design. That's what can happen in industry, and happens a lot. That's where technical people get a bit angry, but it's part of the professional work in the industry. When we select these components, we define these interfaces, and we finish this very important task. After that, we can proceed to so-called detailed design. To detailed design. This is the favorite part of the designers, of course. So I will ask you the following. When we say detailed design, what firstly comes to your mind? You said detailed design of embedded ML embedded system. What firstly comes to your mind? Just say it, doesn't matter. It can be like a wire, doesn't matter.
Schematic development and the PCB layout.
Exactly.
I low level programming, I guess. Structure.
Yeah.
Or language.
Yeah. Okay. Yeah, this is good approach. So yeah, we as a hardware designers in this particular role, of course, we firstly go to schematic design. So we develop a detailed circuit schematics for the system, specifying and drawing all components and their connections in a CAD tool. Of course, CAD tool, computer-aided design. That's what we use. Can you name some of the CAD tools which are commonly used today in industry?
Altium, KiCad.
I heard Altium KiCad. Okay. Altium is really used. Altium is really used. It's one of my favorite tools. KiCad is also used. I can also say that, but not for let's say complex designs. When I say complex designs, that I refer to high, for example, designs with the high-speed digital part, with some let's say analog parts also integrated in the same device, and so on and so on. But it is used. Do you know some other tools? Cadence. Yeah, that's a heavy artillery. Yes, exactly. Okay. So yeah. Sorry. Okay, it was just echo, most probably, because I can hear sometimes echo from there. Okay, so imagine that we finished schematic design. We finish it. What is the next phase in a detailed design phase?
Simulating and yes, I guess simulating.
Good, very good. So we simulate critical circuitry, such as power supplies, analog or RF front ends, in some kind of a space simulator. That's what we do. Simulating power supplies nowadays becomes mandatory. Do not apply reference design without doing a proper simulation. That's my very strong advice. Do not do that. Always simulate. Then, in the data sheet for certain power supplies, you will get some recommendations how to do a layout of the power supply. Do not do differently than that. Trust me, I did it once and never again. Yeah, so when we finish this simulation phase, of course, we then proceed to PCB layout. So what we do there, we design the printed circuit board layout, of course, considering factors like signal integrity, power integrity, and distribution. Then design for manufacturing, testing, EMC, and thermal management. I would like you to ask, how do you understand this thing? Design for manufacturing.
You can.
I understand that design for manufacturing, you said? Sorry, I cannot.
Sorry, can you repeat, please?
You said design for manufacturing?
Yes. How do you understand when someone says, okay, I do also design for manufacturing? How do you understand that?
I guess it is like designing a layout that what data when the product is on the production line that will be easy to build, you know, to blend it to a pick and plate machine, for example, or do something easy for being manufactured. Right. So yeah, check the how the distribution and
The project will need to ask the rules of the FCC, for example, MC rules and intelligent signal were in the same tool. For example, ANSI system you can use for design for manufacturing.
Mm-hmm. Okay. Very, very interesting answers. Okay. So they design. We are referring to something very, very particular here. First of all our designs, they will be manufactured. So someone can think, okay, what does it mean design for manufacturing when we are anyway going to manufacture it? We are designing to be manufactured. But what is generally considered in when you say in the industry design for manufacturing is the following. When you, for example, need to produce like, for example, 10,000 pieces of some hardware assembly, they call it PCB assembly, PCBA. You will also face some problems with yield, or with percentage of properly assembled components. So maybe you have produced 10,000 pieces, but maybe 9,950, which is very high yield, will be actually properly assembled. These 50, they will not work because there was some error in assembly. For example, you have imagine that you have a capacitor, small capacitor, 0402, and when the board assembly was going through the reflow through the oven, then that component finished like this. You know, it was not on the pad. It is called tombstone. It was like this. So it was not soldered. And then it was some very important component, like it was like a series termination of some link or whatever, and then the link doesn't work, and the device does not perform as expected. And you firstly need to pinpoint the problem, and then you need to rework the board to make it functional. All that takes time. In volume production, in mass production, you tend to decrease these kind of things. And this is what is important. Design for manufacturing. There are specific rules, set of rules, which you need to apply when you are doing the layout, so to prevent these kind of things, to prevent that your components go up, for example, to prevent that your components are not soldered properly. I will talk about this later in detail, but just to give you an example, it is like besides functionality, you need to design the layout in such way that you provide a very high yield, so that ideally all of your boards work. So that there is no problem in soldering, in assembling your PCB when you do that automatically on pick and place machine and going through reflow, for example. That's what we call design for manufacturing. Okay, they're also designed for testing. That means that when you design your PCB, that it can be tested. That means that you have a certain set of test points properly placed on the proper subsystems, and your testing coverage is very high, so that you really, when you perform your test, you detect all the failures or almost all the failures. That's how assess your testing is good, which happened during the production. Design for EMC means that you apply also some design techniques which will prevent your device failing on EMC tests. Someone mentioned FCC, yeah, that's US, let's say, testing standards for EMC, which you need to pass in order to sell your devices on the market in US. So if you apply design for EMC at the very beginning of your design phase, then it means that most probably you will pass these tests. If you don't pass, then you will need to do a redesign. A redesign will incur additional costs and time, and your managers will not be happy. So keep this in mind. This will save you most probably in your professional work. Okay, so we covered this detailed design phase. This is from theoretical part. And now we are at the phase which is called prototyping. So we finish with the design, we generated production files, and we send them. And we now expect to get the PCB to test, to see what we designed. Okay, so we need to build a prototype. Once we get that prototype, we need to perform functional testing, performance testing, and environmental testing to validate the design against the requirements. This sounds very easy. This sounds straightforward, but actually this is a very problematic part. This is where hardware designers and firmware designers come together. Hardware designers, they know the platform very well because they design it. Firmware designers need to download their code they develop for the platform, and they need to do so-called bring up of the PCB. That's where these two groups collide. And that's why I said, if you are, for example, in a firmware group, if you do not understand the hardware, it will be a very painful process for both teams. Very painful process and very long process. In order to, of course, do proper testing and validation, before that we need to, of course, define the test procedures and pass-fail criteria. Pass-fail criteria is very hard to define. You will hear many inputs from many groups, including customers. And align and agree on this pass-fail criteria is pretty hard. It's not a straightforward task. I will just say like that. Okay. Firmware development. So we need to develop the software that will run on the embedded hardware, including bootloaders, device drivers, and application code. This is where we are currently, application code. Once we finish that, this is also a painful thing because it will require interaction between the teams. And I again emphasize, if firmware guys do not understand hardware and hardware guys do not understand firmware, at least at some level, problems, always problems. When we finish these parts, then we come to integration testing. So test the firmware with the hardware to ensure proper operation performance. This will be tested in a different conditions, not only putting on a table, laboratory table, and test and see what's going on. No, it will go through different to temperature cyclings, to some other tests like immunity tests where the device will be exposed to some interference and so on and so on. Once we perform this, we are ready for optimization. So performance optimization, optimize the hardware and firmware for performance, power consumption, and cost. Most probably the cost will be the most painful part. I have advice here. Start with the components which are, let's say, slightly expensive, which are already tested, which are proven. And once you have that functional, you can show something, especially to the customer, then go to lowering the cost and try to come up with some, let's say, cheaper solution. By the way, that's not always possible, but always try to do that. That's a good approach, and it will save you. Then we will iterate on the design. This is normal thing. So iterate on the design based on testing feedback to address any issues and improve the systems. Sometimes even happens that you do iteration when you deploy the device, and it's the devices have been already working in the field for some time. These are extreme things, but they happen. And when they happen, it's a very big problem for the company. Okay, when we finish these design iterations, we have so-called final testing and validation. Final. This is a moment of truth. This is where you will face so-called compliance testing. So ensure the design meets all regulatory and compliance standards. Of course, we do these kind of things. I'm also responsible for EMC tests in Teledyne here in this company, and I go to the EMC labs to perform these tests. And I talk, of course, to the personnel there, to their test engineers. For example, once I asked, based on the experience of one lab here we have in a high-tech campus, what is the percentage of the devices, of the systems, which are brought to the tests, which pass the compliance test very first time? And the answer of these test engineers there who test these devices on daily basis, they say approximately 30% of the devices pass these tests from very first time. This is a big problem, and yeah, you will face this in the practice. There are also reliability testing, so conduct long-term reliability testing to ensure the system will perform as expected over intended lifespan. So maybe you can perform some tests, they call it like accelerating aging. So you will perform that on a higher temperature, you will put and keep device on a higher temperature than it is needed, and will perform the set of tests. Then we come to production and deployment. Manufacturing preparation. So prepare the design for manufacturing, including creating detailed manufacturing documentation, and selecting manufacturing partners. Usually what will happen to you is that you will have a limited suppliers when you work for a big company, because big companies, they tend to have a list of suppliers and you cannot select whatever you want. You work just with these suppliers on the list, and that's all. That's a constraint. And my advice is, when you come to a company, when you start to work, get acquainted with these kind of things. Get acquainted. When you get this list, check these suppliers, their capabilities. It's very important because they can limit your design. Production testing, so implementing testing procedures for the production line to ensure each unit meets quality standards. This is what we mentioned even before when you do design for test. So you need to think in advance what will be needed to be tested once your device enters the mass production. And of course, finally, we get to the deployment. So what will happen? And it will happen that your device or devices will be in the field operating. They will encounter some problems from time to time. Support team will try to resolve these issues, but sometimes these problems escalates directly to design teams. So be also ready for that. And finally, I will give you just some best practices. I like to say this: there are numerous of best practices, and you will hear different stories from different people who work a long time in industry. But I will highlight only 3 here, and I think everyone will agree on that. So first of all, documentation. Engineers hate documentation, documenting the things. I know that. Maintain thorough documentation throughout the design process to ensure clarity, and more importantly, to facilitate future maintenance. So what will happen? It will happen that you will be switched to another project, and some things will escalate from one of the previous projects. You will forget almost everything about it, and you will not be able to cope efficiently with the problem. And what I would also say is, when you are designing, keep in mind the following thing: modular design. Either you are writing a firmware or you are designing a hardware. Always keep this in mind, because you will make your life easier. So design the system in a modular way to allow for easier updates and scalability. That's very important. And the last thing, very, very last thing of best practices will be the following: risk management. So to be honest, when I firstly hear this, I hated this procedure, risk management. I really hated it. I found it just an overhead which is useless, basically. So how this looks like in industry: you will get in a room with a team which is responsible for these kind of things, and they will ask you what kind of risk you see related to this part of design, to this part, that part, that part. So I have a colleague, he says, if I could see all the risks, then I would not make such mistakes. But actually, these sessions makes you think in advance. And if you think in advance, you can maybe prevent problems. So I will not go into more best practices. You can hear a lot of stories, this, that story, and so on. I will just stop here, and I will ask you if you have some questions. Okay, if not a question, I have a question for you. Was this kind or this presentation too boring for you?
Sorry, I had 2 questions.
Okay.
In that live played me out, but it was in an early stage. If you can go back to the slide of simulation and PCB layer.
Yes.
Because it came to me there how often does it happen that these tasks that appear to be in that order get like overlapped in time, like the simulation phase didn't end yet, but someone starts on working on the PCB layout. How often does this happen along the entire phase of design?
Very, very good question. So I will tell you how it works in practice, at least in some of the previous companies I worked. So you, for example, do the this phase. I will go like this. Key component selection. Layout team already starts to design libraries with these components, and they already start to do initial position of the components, key components. You didn't even make a full schematic. They already started. That firstly, what happened? That's the first thing. Then you proceed with the schematic design. Okay, they finish some initial component placement. They determine the number of layers they need to use. They determine dimensions if they are not constrained by some mechanical constraints from mechanical team in the dimensions. You proceed with the schematic, you finish schematic, maybe they finish their part. Then you say, okay, now I need to simulate, for example, power supplies. They already started to lay out power supplies. Then you, for example, see that some, I don't know, some capacitors, some feedback loop is not properly done. Okay, you change the components. Layouters, they complain a bit, but basically they don't care. They do these changes. Then you finally finish this. Layouters are just working. And then they come to the we come to the PCB layout. That's another thing, because usually in what you will face in most of the companies, not all, but most of the companies, you will face that you will work either for schematic team or layout team. They are separated. You will not work on schematic and then on layout. These are separate teams most of the time. In this group where I am, it's not, but most of the time it is. What will happen in the PCB layout? They would need to perform some simulation, as I wrote here, simulate critical parts, for example, high-speed digital parts of the layout with 2.5D or 3D field solver. Someone mentions ANSYS HFSS. There is also C-Wave from ANSYS. It's faster, it's 2.5D. They design, but they don't perform, for example, the simulations. They do not verify the high-speed links, but they send the design to production, because always problem with time. Managers comes, he says, yeah, we need to send it. And he say, yeah, but we need to simulate. Okay, I trust, yeah, we will sort it out later. Just send it. We need to have hardware to present. Hardware comes. Most of the time links will work, high-speed links, for example, but it can happen also that they don't work. Problem. That's how it functions in industry. Okay, so I think it's a time for a break. Let's make a break of 10 minutes and let's do the last session. I hope that you didn't find this too much boring. I tried, because this is methodological stuff. It is by default can be boring, you know. I tried to put some spices here and there. Hope you didn't get too much bored. See you in 10 minutes. Yeah, we are starting again. Hopefully you survived the previous presentation. Yeah, methodological designs and stuff. Always, yeah, can be boring, but okay. So far, what we did, we just give an overview of the key components and some architectures used in edge ML devices. We also tackled a bit in methodological way hardware design. We explained some things, and we also tackled some problems which are encountered in industry in practice, and you will face them as well. And now we are going, let's say, more or deeper. We are going to tackle some practical hardware design considerations for embedded platforms in machine learning. I will share my screen. I hope you can see it. Okay. Super. So, practical hardware design consideration for embedded platforms in so tomorrow we will also continue with this. So what we are going to do here, we are going to explore the key design aspects of an edge ML system for distinguishing between gamma rays and neutrons. So this system has been implemented. This is the system I mentioned in the beginning. This hardware exists. This device exists. I was involved in the hardware design. Romina wrote some algorithms to ML algorithms to actually distinguish between these gamma rays and neutrons. And I'm going to walk you through that design, but I'm not going to present you just what we did. I would like your interaction because this will help you for the exercise you will have the last day. This will really help you. So let's see. I will give you, I call them very simplified requirements for this system. Very simplified requirements. It will be on 2 slides. Try to remember key information, because what we are going to do after this is I'm going to draw and you are going to design the architecture of this device. I would like to see how you would do that, because maybe we did not do that in optimal way. And maybe you have some better ideas. So what are these simplified requirements? First of all, we have some requirement for power supply. This device needs to be powered from both lithium polymer battery and external 5-volt source. This device needs to charge battery when we are connected to external power supply. So this is in terms of power supply requirements. In terms of the connectivity of the device, I here primarily refer to connectivity to outside world. We need to have like a USB connection, and we need to have wireless connection. But this is specific wireless connection. This is not a Wi-Fi, Zigbee, Bluetooth, I mean 2.4 gigahertz operations. This is on 433 megahertz, and data rate is 250 kilobits per second. Then, in terms of peripherals, this system needs to have an altimeter, GNSS receiver, temperature sensor, and there is a special request for the memory. This memory is not connected with the basic operation of the board. This is dedicated onboard memory to store measurement data. So on this slide, we have power supply, connectivity, and peripherals requirements. We will get back to this if necessary. Very simplified requirements, second slide. So I define this as additional requirements. Platform needs to be operational both as a standalone device in the lab, in the laboratory, but also this device needs to be capable of attaching to the UAV, to the drone. Second thing is platform needs to source programmatically adjustable voltage, 30 to 35 volts, 5 milliamps. This is used for a sensor, for gamma detection, neutron detection. And its external component. You don't need to think about that component. We just think about the processing part of the system. External component, just think about that as a black box. It's just sensor which sends analog signal. So, as I said, platform needs to analog front end to convert signal from silicon photomultiplier to digital domain. Just to give you a brief explanation how this works, very brief and simple explanation. So you have a sensor which is called scintillator, some like similar to some plastic material, for example, and it's transparent. And when the gamma rays goes through it, it will just create photons. It will just create some light, like a flash. And then we use this silicon photomultipliers, these diodes, to convert that to current. And then we will use in analog front end some transimpedance amplifier to convert that to voltage, to put that to the ADC, and then to process it somehow. Do you have questions regarding this platform requirements? Should I go back once again? So power supply, we need both battery, lead poly battery, and external 5-volt power supply. We need to enable battery charging because battery is the part of the system. Battery charging when it is connected on a 5 volts externally. Connectivity USB connection and wireless connection. Peripherals, altimeter, GNSS receiver, temperature sensor, and onboard memory. And then these, I call them additional requirements. So operational as a standalone device. So obviously you will not need in the laboratory altimeter or GNSS receiver. Then you need this programmatically adjustable voltage, 30 to 35 volts. And of course, this analog front end. So let's go firstly like this. Like we will have a general discussion and selections of key components. So what would be actually the main goal, of course, select main processing points which can fulfill the functional requirement. So to do so, we need to first understand major platform deployment constraints, and this will help us narrow the selection. So if I ask you, what are the major deployment constraints, what would you ask? What would you answer? So think about where are we going to deploy the device?
You know the environment when
where you deploy the device.
Can you repeat, please?
That you have to know the environment that you deploy the device.
Yeah, but in the requirements we said actually where it's going to be deployed. So it's going to be deployed on UAV, but it can also be deployed as a standalone device in the lab. So when we say it is going to be deployed on the UAV, what major constraints you see there?
The analog signal characteristics.
What the analog signal characteristics?
I don't know, amplitude, speed, or bandwidth.
Mm-hmm. So what I would say, if you would ask me this question, I would say, and based on power supply requirement, this device must be this is battery operated device. It must fulfill that requirement. It is battery operated device. And because it is on the drone, this battery, okay, it can be big, but I suppose that because of the range of flight of the drone, we would like the load to be very light. So we don't want a big battery. And we don't want to use battery from the drone. We want a standalone device in that sense. So that tells you something about the components which are going to be used as processing components. It tells you something. You most probably are not going to deploy GPU there, most probably. But on the other side, because you can use that device in laboratory, so you will put that on a table and you will, or near some source in a laboratory, and then you are going to do some measurements, you will have like external power supply, unlimited external power supply. But because you have these two opposite requirements, of course, you need to accommodate it for battery operation. That's one thing. What we can see here. And what we can infer is that we cannot use some high computationally powerful devices. Secondly, we need to understand how much processing computational power we need for this. How are we going to tackle this part? How are we going to understand this?
I don't know if it corresponds to this scope, but I think that I would take a relevant or realistic use case and from some simulation, like system level simulation, get some idea about the amount of processing, the power of processing I need to fulfill my realistic or relevant application use case.
Mm-hmm.
So
yeah,
I would expect to get some information about that from system team. Again, performing some system level simulation, providing relevant use cases, and from that get the estimate about this computational.
Yeah, that's the right approach. That's the right approach. Okay, so yeah, so this is how are we going to tackle the problem. So we firstly understand the major platform deployment constraints. Secondly, we need to understand how much processing computational power we need. If you ask ML engineers, they will say, no, we need firstly to understand how much processing computational power we need. And then we will think about the key processing components. These are collisioning requirements. And that's why we emphasize some things at the very, very first presentation today. This is why it is important to understand, at least to have a rough idea of what's going on in a cross-functional team. to avoid these kind of collisions and these kind of discussions. That happens a lot. Okay, so we firstly have general discussions, selections of key components. When we do that, then we go where? To key component data sheet and reference design analysis. So we somehow selected key components. We did the data sheet and reference design analysis. That's very important. And what is written here is, it says that this step is crucial because it allows us to restart the selection of the key components due to insufficient documentation and support. I will tell you some tips from the practice. So what is usually done in industry, you are not going now to design some schematic from scratch for these key components, for example, for some, I don't know, processor, microcontroller, FPGA, whatever. There are reference designs already done. And what engineers usually do, they use these reference designs and they blindly copy them into designs. Okay, they scrap some things they don't need because these are usually platforms, you know, which has a lot of peripherals. They want to demonstrate the capabilities of these components. So they put everything, you scrap that, you just put parts you need. So you are not going now to design that from scratch. But be cautious there, always analyze. Do not do that without thinking. Analyze what is inside. And there is another tip. If evaluation boards are available, they are typically ordered at this stage for assessment by various teams, by hardware, by firmware teams. So they can evaluate actually the characteristics which are given in data sheets, because you will see that sometimes the characteristics, the performance is not actually what's written in these documents. Okay, so once you do that, once you finish this and you have your key components, then you come to the my favorite part, power consumption calculations. So what we do, we calculate the worst case scenario in terms of power consumption for key components. For that, you need to consult data sheet. You most probably need to consult support of the manufacturer of the key components, and you will get some data. If you have an evaluation board, then you can measure it directly in that system, even deploying some code there, which resembles to what you are going to do in your application. So when we calculated this power consumption, then we select the components which will be used to implement these power supplies. So we need to select these components. And now I have a question for you. So you saw how many rails are necessary in the introduction presentation. You saw, for example, how many rails you need for a simple a microcontroller which has a small hardware accelerator inside, for example. You saw how many rails you need for FPGA, for NPU. So you see there are quite a lot of rails. So how do you tackle the design of complete power supply scheme? How would you tackle that? There is systematic approach for that actually, and very useful. What do you need to do actually? Do you have an idea about that?
You mean about the layout, or you mean about?
No, we are not in layout phase. We are just now in a consideration phase. We did not start to design anything yet. We are not in the design phase if we refer to this methodology what we presented in a previous presentation. We are still not there.
I've checked if there's like an integrated circuit that has multiple outputs, like a PET, like a PMIC, that has multiple rails outputs.
So you need to consider the difference between getting that type of system or design your own power modulation unit. That is the thing you're asking right now.
Yeah. So I'm asking the following, and I will tell you how you, because you saw these number of rails. You are now acquainted that you need to provide the sequences of these rails. You will start some power supply rails before, some later. Some will be tightly related to previous one. To understand that properly, you need to make so-called power tree. Power tree. It is called power tree. So you just draw the input source, and then you make all the branches, and you make all the dependencies there. You draw that, and that power tree is actually, let's call it like a power supply architecture, and it's a separate topic. You cannot tackle these kind of problems anymore in some way it was done before, where you have one or two rails and that's it. Now it's complex, and you really need to pay specific attention to that. So finally, we designed the power tree for the platform and simulate power supplies. Mandatory. It is mandatory to simulate. We said that already. So you can use this, for example, LT Power CAD for drawing a tree, and you can use some SPICE-based simulator, LT Spice or whatever, to simulate these the power supplies. That's what you really need to do. When you finish with this part, then you can come to system architecture. Then you are able to proper system architecture. When you finish all these parts, discuss them, understand all these things, then you can make system architecture. So before we proceed, I'll go just briefly once again to this. We have at the beginning requirements. We finished somehow that part, customer with some third party, and we got something. These requirements are not done in this way. This is overly simplified. That is a document. That is a big, it can be very big document actually. This is just for an, let's say, educational example. But in the practice, it's a real document. Okay, we see the requirements. Step one, we have a general discussion and selection of key components. So what we do there? Okay, firstly, understand the major platform deployment constraints. We need to understand where this platform will be operating. We need to understand constraints in these environments. We need to somehow bridge the gap between these constraints. In this particular case, we have UAV and we have a laboratory to work. Quite opposite environments. Then, of course, we need to understand how much processing computational power we need. These are some basic things we need to understand in order to select key components. Key components are components used for example, processing, some for, I don't know, power supply, for storing the data. So all these components we cannot, I would say, easy to integrate into the platform. They are not, let's say, straightforward, especially they are high speed, and they are. So that's the first step, just general discussion, and we need to come up after that with the key components. Once we selected key components, we go to the data sheets and reference design analysis. So there are key components which doesn't have reference designs. Are you going to use these components? Basically, no. But yes, if you are forced to, if the bill of material, if the cost of the system is pushing you, you are going to use them. But basically, what are you going to do? You are first going to check that, because you will make your life easier with that. Simple as that. Okay, that's a crucial thing. Of course, if evaluation boards are available, that's a plus. That's something that then you really can check the specification of these components, if they really fits what is written in the documents. Okay, so we analyze these data sheets, we analyze reference designs, that's okay. We fixed key components, then we proceed to power consumption calculations. We said we are going to consult data sheets, we are going to consult manufacturer of these components. They have their support, big companies, they have even their direct contacts there. You will get information very fast. If you try to do that outside of the company as for example, some enthusiast or hobby, you will most probably never get any answer from them, but within a company, you will get them. And you most probably have, as I said, direct contact there. When we finish these calculations, then we select the integrated circuits we are going to use, and then we design this so-called power tree. And after that, we are ready for system architecture. We are ready to come up with the initial version of the system architecture. Today's task for us will be to come up with something. It doesn't, when I say with something, it doesn't need to be a proper architecture or the architecture which really can do these things, but we need more or less to be there. What I'm going to do now, I'm going to share my whiteboard and I'm going to start drawing. Just a second. Okay. This is here. Can you see this screen now? Can you see me writing something?
Yes.
Excellent. Okay, guys. Let's start. What would be the key components here, based on your intuition, based on your previous knowledge, based on what we said now? This is a tough guess, of course. This is like, don't expect that you will give a 100% right answer, but maybe you will.
I'm the process engineer, yes.
CPU, I heard somewhere CPU. Yes, okay. Let's put CPU. Let's stick to the basics. CPU. Okay, what are we going to do then?
Memory.
Sorry, what?
Memory.
Memory, okay, memory. Which type of memory? RAM memory. Okay. Then what are we going to do?
We need the sensors as well.
Sensor. ADC. Yes. We need ADC.
The amount of IOs that I will need to connect all the sensors that I will use.
Sorry, can you repeat once again? I didn't hear.
Amount of boards or IOs to connect all the sensors that I'm going to use.
Actually, I will help you with the sensor because it's very application specific. We will just say sensor here. Just say sensor.
Sensors are integrated into the PCB.
Exactly. Sensor. I will do like this. Okay. Then what? What did you say?
Connectivity, wireless connectivity, USB connectivity.
USB. You want to say USB? Okay, we can say like this. USB port.
Also, power supply.
Okay, we will need to work out power supply. I will just put the block here, but we will need to work it out.
Like a PMIC to be able to choose between the supply from the USB ports or 5 volts or the batteries.
Very good. Very. I will put it like this. And I will say like this. And I will say battery. And then we come here. So that was a good observation. We need a PMIC which will arbitrate between this guy here and this guy here. And when this PMIC finish job, then we will deliver stable power supply to our power tree, which further delivers power to the whole board. This is good thing. If I were you, I would do this part as a very first thing, for example. But okay, this approach is also good. Let's continue.
Sorry, you said you would do first the power supply part.
Yes.
Yeah. Okay.
Yes. So I will just tell you how I think. Maybe it will help you. I think in the following way. When I'm thinking about design, of course, I firstly tackle the power supply scheme, the power supply tree, how I provide the power supply. Once I resolve that part, that I can deliver clean, let's say, power supply, then I tackle other things, how to connect. Of course, when I do this, I have in my head the whole picture. That's also important. Otherwise, you cannot do this part. But okay, this is also a valid and good approach. You start with the inside out, let's say like that. It can also be tackled in that way. There is no problem with that. Not at all. It is actually a matter of personal preference, nothing special. Okay, so we proceed forward. We have PMIC, which will arbitrate for input power supplies. We said CPU. We said RAM memory, ADC, and sensor. So what did we say about connectivity and peripherals? Can you remember that?
We need the 433 megahertz wireless.
Yes. So do you know some components which can perform that? Do you know how they are called in general? You heard for example, Zigbee, Bluetooth. You know about these small modules. You can buy them. You most probably use them. there are also modules rated at different frequencies, not only 2.2, and they do not use kind of protocol. They are simple. So basically, you define your own protocol. You have just a physical layer. You have just a transceiver. So it is able to modulate, send, received, and demodulate. That's all. And there are a bunch of these chips. So we will call it just RF transceiver. We'll put it here. The data rate this needs to go is 250 kilobits per second. What kind of interface you would looking for if you want to connect this transceiver to the CPU? What kind of bus you would use here? Sorry?
Differential bus.
Differential bus. Why that? Why would you use differential bus?
Because the noise.
Sorry, because of?
Because the noise this bus.
Okay, I understand your point. Yes, differential signaling, it is more immune, or differential ended signals, they're more immune to external noise, because they will, in ideal case, it will be cancelled. But what I forgot to tell you is this transceiver here, it has RF front end inside, and it also has a digital part here and digital interface. So inside you have circuitry which will actually put this received data in the digital domain, and you will have purely digital signal out of this transceiver. That's one thing. I will just tell you that in this domain, for what we are talking now, I didn't see a receiver or transceiver which has differential outputs. Most probably because it would be like a big overhead. Maybe it's not necessary in this case, because the speeds are also very low. So you have plenty of time to decode these pulses. But does the information 250 kilobits tells you something? Which kind of interface you could select?
DMA
Or the bus?
DMA communication.
DMA, direct memory access. Okay. Yeah. Yeah. Well, you know what can be used, and what is usually used is simple UART. Simple UART is actually connected to this component, what we named here CPU. Why UART? UART is used because we have here low speeds. We have part here which is purely digital, and it just provides digital information here. So we don't need to worry too much about this. Sorry?
With a serial bus.
Now, I didn't understand which kind of a bus.
Serial bus.
A serial bus. Yeah, I mean this is a serial bus. This UART, if we say like this. That's all what we need here. Basically, these components, they are modules. Usually they're made like modules. So you will have interface UART. If you just purely use the integrated circuit here, you will have something like SPI, or you will have something like I2C. But okay, these are so standard interfaces. They're used everywhere. On when you have PCB communication, then on the PCB, then you will use one of these interfaces. But let's check what we have here between CPU and ADC. This can be a bit tricky, and someone already said a solution for this. He referred to this kind of receiver, but actually it's not used there in this particular case, but used here. Sorry? I didn't understand.
Differential?
Differential. Yes, differential. We have here differential transmission. We have here LVDS pairs. Just say like this. And this is, for this kind of application, you don't need to know that, and it's not of the importance for this particular workshop. This will be 250 megasamples per second. This is a bit fast, and we need differential transmission here. Okay, we need now the altimeter. So how would you approach this problem? What kind of component you would select there? Are you going to select like some external component which will be connected through some connector to the PCB, or it will be some kind of integral part of the PCB you are going to implement it by yourself? What would be your general approach here?
Sorry, can you come again? I didn't hear the first.
Yes. Yeah. So you need to select now the altimeter for this system because there is a requirement for that. This is due to the fact that this platform will be deployed on the drone and some measurements will be done, and you will need altitude in order to calibrate the measurement. It's out of the scope of this, but doesn't matter. So, and my question is, what would be your approach in selection of this component? Would you go in the direction that you find some external component which has some interface which you would connect and use and connect it to the PCB, or you would implement some kind of measurement system on your PCB?
Size is a constraint. I would try to implement it inside the PCB.
On the PCB, you mean? Okay. Okay. Yeah. So I will tell you what approach we used. We checked and we saw that there are components which are relatively small and they will not pose some overhead in terms of weight. So in order to simplify that, we opted for external component, which again has, believe it or not, UART interface. So there is altimeter, but is connected via and this would be UART again. It is simple and it is expected because you will just send the height. It can be a number, a few bytes. Just a few bytes, and UART is enough for that. Okay, what does this system lacks? So we resolved this part is properly, really properly resolved. This part is now resolved again properly. This part is resolved now. This part is resolved. But now we need to get to the to go back to the basics. What this system needs more in order to be operational.
Memory.
Yeah, some nor flash, for example. Nor flash, or to store the code. Okay, and there is also one specific requirement. We need to have onboard memory, dedicated onboard memory, which will actually store the measurement data. I can put some non-flash maybe. Non-flash for that. Why is that used? Well, while you are flying with this device, you will try to send your data in real time throughout this wireless connection. But it can happen because it's wireless transmission. It can happen that you lose some packets, and you don't want that, of course. What you are going to do, you are going to do data storage in parallel. So you will, for example, send the data and store them, send the data and store them, send the data and store them. And then you can compare the data when the flight is finished and just see if you missed something. Okay, so more or less, we are there. There is some small things we need here. Some very small things.
Program the CPU.
Yes, debug board. Do you want maybe some debug UART that you can, when you start debugging your application, that you have some easier life? Yes, you will have some debug UART, for example, just for write-outs. Maybe you will have some LEDs. That's also good to have. Some dirty small thing which eases the debugging sometimes. Okay, and do we lack something else?
For the programmable voltage requirements, that would be the same power supply in charge of that, or should we use a separate?
That would be a separate power supply. It was let's say specific request because it said that this PCB, this device, needs to source that power supply. So basically, that power supply is used to power supply the SIPM diodes, and that's basically all, more or less. So I will just say like SIPM power supply. Okay, this is just initial discussion. This is what we would have in the practice as a very, very, very first discussion. In practice, this would be refined many times due to technical reasons, due to customer requests, due to some other requests. It will be refined many, many times. And then you would come with some architecture which will be fixed, and then you will be able to proceed according to the methodology we actually presented in a previous presentation. But this is very important task, and this is a milestone, because now when we have this fixed, then we can proceed, to design. Basically, we can proceed to design. That's more let's say interesting part. Okay, so what I would say now, because it's 2 o'clock here, at your is like what is it your time? It's 9 o'clock. I would say that we are on time to finish this part and to finish for today. Tomorrow I will present you the architecture of the actual architecture of the design, how it looks like. We will analyze it. I will explain you why we selected some of the solutions, why we did in that way, and so on. And then we will tackle the design, of course, from the practical perspective. I will walk you through the design. I will have some. I will have a real example in Altium. I will show you some things, but don't worry, it will not be a boring thing. Like I opened a project, like some tutorial, not like that. It will be different. It is differently tailored, so you will not get bored. Okay, so I would like to thank you for today, and see you tomorrow at the same time.
Thanks a lot, Nicola.
Thank you.
See you tomorrow.